And we're back, continuing to find our centers. Up to this point, we've been dealing with individual objects like a rod, sheet of plywood, triangles, curves, whatever those we would use calculus for. When we started out using algebra, we had individual pieces that were all connected on maybe a meter stick or the entire solar system's mass. Those locations, just add those up and divide by the mass whole. And now we're going to take a look at something a little different. We're going to take those systems of particles, those masses, like all of the solar system, and as those items are moving, what does the center mass of those items do? So that's what we're going to deal with. If there's a system of particles, if there's 3, 4, 5, 9, 10 objects all hanging out together, those objects have a common center mass. And as those objects move, what does the center mass do? That's what we're going to find out. So again, we're going to deal with, we got some momentum, we got forces, we got impulses. So you could deal with Mo in questions like this. You'll have questions that deal with Mo. Remember, Mo is P and it's mv. The sum of the momentum on any given individual particle in there, add it all up, you will get a capital M. Remember, the big M means the mass whole, the mass of the whole system, every particle put together, multiplied by the velocity of the center mass. That center mass acts as it is all of the mass at that one location. So whenever you're talking about the mass whole, you're talking about the center mass. So the velocity of the mass whole is the speed of the center mass. You can get that again by adding up all of the momentums of each individual particle. Just remember, you add them vectorially. So when it says push the plus button, what it means is push the tail to tip button, and you'll get the mass whole times the velocity of the center mass in whatever direction it happens to be moving based on its mo. You can do the same thing for forces. You have F equals ma. Someone should make a law. In this case, the FR stands for resultant force. So the direction of the resultant force gives you the mass whole times the direction of the A whole, the acceleration of the center mass. All right, that center mass again acts as though all of the mass is located there. So that's where the mass whole hangs out. Then you have you could do it the same way as we did up there. You can add up the MAs of each individual particle. In that system of particles, it will add up to the mass whole times what the acceleration of that mass whole is doing, the A whole. Okay, remember, this again is a vector, so you push the tail to tip button if you need to, and it gets you that vector. Remember, impulses are what change momentum. It is a force times time. That R again means the resultant force, so that FR times T. When these forces are vectors and they add together to give you an impulse, that is a vector also. So you can add up all the individual pieces of that system to get what the center mass, what the whole system is doing. This is the example we're going to use. Let's pretend in our heads there's these three masses here. One of them is 4 kgs, one of them is 8 kgs, another one is another 4 kg mass. This one has a force applying on it of 6 newtons. This second force is 10 newtons acting on the 8 kg mass, and on this bottom mass down here, there's 14 newtons acting on it. This one starts out at a location, what, a -2 and 3. This one starts out at 4, 2, and this one starts out at what, 1, -2. So what I did is I put a dot at their common center mass. You don't need to know what that mass is or what that location is, but if you guys want to do a bit of a review, go ahead and figure out that the X center mass happens to be 1.75 in this particular system, so it's there. The Y center mass happens to be 1.25, which is right there. So anyway, that's where all three of those masses are centered. So as those three masses start to move in their respective X and Ytions, where does the mass whole go? What does it do? What does the center mass do? So there are several different ways you can do it. One is to add up all the individual MAs and then triangulate. Well, we are going to triangulate because these are vectors and they have direction. So the way we could do it is Newton's second law. Sum of the forces equal ma. So if we start out by getting the acceleration in the x, which you could also say is the I, right? The acceleration in the I and in the j and in the k. But the ma, that net force in the x, is equal to the capital M times the acceleration. So what are the net forces in the x? There are two forces acting in the x. F1 is 6 newtons, and it's in the negative x. And F2 is, F3, japers, F3 is 14 newtons, and it's acting in the positive x. So what I'm going to do is I'm going to put 14 and 6 together, tail to tiply, so when I add them, I'm clearly going to be pushing the minus button. So this is 14 newtons minus 6 newtons. Those are the net forces in the x. It will equal the mass whole times the a whole. So if I want to get the acceleration in the x, what I'm going to do is divide those by the mass whole, which the mass of this whole system, add them up, it's 4, 8, and another 4. So I'm going to call that 16. So there's 16 kg. So 14 minus 6, I'm calling that 8, divided by 16. The acceleration in the x is 0.500 meters per second squared. That's the acceleration in the I, if you wish to call it in unit vector notation. Okay, remember it's the net force, but if we're talking about the center mass, we're talking about the mass whole. All right, we can do the same thing for the ma and the y. Now in the y, or the j, there's only one arrow. It's the 8 kilogram mass being pushed upwards by F2, which is 10 newtons. So the sum of the forces in the y is the sum of the forces in the y. It's simply 10 newtons. But I'm going to take that 10 newtons and I'm going to divide it by the same mass whole because it's the same system of masses. So I'm going to take that 10, I'm going to divide it by 16 kgs, and the acceleration in the y then is 10 divided by 16. That turns out to be 0.625 meters per second squared. So now I have an acceleration in the x and an acceleration in the y. And what we will now do is simply triangulate them. Get Pythagoras on the phone. There's your acceleration in the x. There's your acceleration in the y. So this acceleration of the center mass then is just 0.5 squared plus 0.625 squared square rooted. And it's nothing more than 0.8 meters per second squared. All right. To get the direction, remember you would lay out at night to get the direction of this particular guy, which I had forgotten to do here, but jeepers. I'm going to take the second tan of the acceleration of the y, 0.625. I'm going to divide that by 0.5, and I'm getting 51 degrees. So to get that angle, we will lay out at night. Take an inverse tan of 0.625 divided by 0.5, and the angle ends up being 51 degrees. We would communicate that north of east. All right, so this is one strategery in which I put the division divide by the mass whole before I triangulated. Some students would prefer to divide by the mass whole after you triangulate because this triangle is made of accelerations. It could be made of forces, just forces now. So what are the forces in the x? If all I want to do is just get forces here, forces in the x are nothing more than that F1, which is -6, and F3, which is +14. So if I want just the forces in the x, it's again going to be that 14 minus 6, isn't it? So the force in the x is 14 newtons minus 6 newtons. So that's going to be 8 newtons, right? The force in the y, remember that was 10 newtons, so that's all, there's no adding, there's 10 newtons. So what I could do is make a triangle of 8 and 10 and get the net force. That's the resultant. The FR is the net force, and this is going to be 10 squared plus 8 squared, square rootified, and this ends up being 12.8 newtons. All right, that 12.8 newtons now is the sum of all the forces and both the dir x and y shin, and that force is acting on the entire system, the mass whole, because there's the F whole. Let's now find the A whole by dividing by the mass whole. So that force is going to be 12.8 newtons, the resultant force. I'm going to divide it by the same mass whole we've been dealing with, 16 kgs. And so 12.8 divided by 16, son of a gun, if it's not exactly the same thing we got up here by calling it 0.8 meters per second squared when we did the triangle here, 0.800 meters per second squared. So you can divide by the mass whole before you triangulate, or you can divide by the mass whole after you triangulate. It's up to you. It doesn't really matter, okay? And here's what I will do. I will add one more question to this set of stuff, and I'll have you do 15 also. So the Green Book, Chapter 9, 13, 14, 15, and I will give you I will post those pictures, and as I post those pictures, I'll give you a couple of tips on how to work your way through these. Number 15 has a video posted in your folder already. I worked that one out a few years back, how to go through answering that particular question. But again, this one is the next section. We're just going to keep moving, finding our centers here. Just because there's a system of masses that move doesn't mean the mass whole doesn't move right along with it. The center certainly does. In this case, for this particular set of 3 items, this center mass, as these guys move, this center mass will accelerate that way, which we said was 51 degrees, and its acceleration is 0.8 meters per second squared. So all 3 of those, even though none of them are moving in that direction, they add up to what the mass whole does, move in that direction. 51 center mass, the 51 degrees at 0.8 meters per second squared. So it's kind of neat to trace what that center mass does. All right, but anywho, there you go. Hopefully you did just turn in your calculation. It is the center mass of the solar system, provided the planets are lined up, which I know they never are, but it's just an interesting calculation. The correct answer is like 2.2-ish sun radiuses away is where it's centered. That's only if they're all lined up. Another interesting thing is, if you did go through the fuss of adding up the mass of the entire solar system, you started out with the mass of the sun, you got a number, and then you added all of those planets next to it, and when you pushed the enter button, did you notice it still gave you just the mass of the sun? So it's pretty interesting to see those trends. The sun's awfully big. All right, and it was out today. Gosh, it was a beautiful day, and I will hopefully get to enjoy a little more of it tomorrow. But anyway, that's it. Stay centered and yay, physics.